Great, so next up is Wido. Wido comes from the Netherlands, former VP.
Yeah, former VP, 2 years ago.
2 years ago, did a very, very good job. What are you talking about today?
I'm talking about flexible networking using VXLAN in CloudStack.
Cool. Everybody, big warm welcome to Wido.
So, a bit of overview of who I am. I'm CTO and co-owner of a Dutch hosting company. I've been working with CloudStack for 6 years now, no longer, 7 to 8 years. And we're running a CloudStack deployment, a pretty big CloudStack deployment. A couple of things I did, I wrote the Ceph integration for CloudStack for KVM, work on the KVM hypervisor code, maintain the Debian Ubuntu packages, and I have done some basic networking IPv6 integration. And I'm going to be talking about VXLAN and IPv6 integration, which I've done for 4.12. So my company, Dutch hosting company since 2004. We started as a traditional shared hosting company. 30 employees, 50,000 customers, roughly 50,000. And we have a public cloud running on Apache CloudStack. Since last year, my company got acquired. We're now part of a big group called Total Web Hosting Solutions. We're building out in Europe, so we have deployments in Spain, deployments in the Netherlands, in Germany, and it's all going to be running on Apache CloudStack. So, as we are 30, our total group is about 600 employees, and we're transitioning towards CloudStack with the complete group. But currently, 250 hypervisors, all KVM, over 20,000 virtual machines running on CloudStack, mainly in Amsterdam, although we are building in Antwerp, Barcelona, and Miami. We have those, but we're expanding our systems there. But I'm going to be talking about what I did for 4.12 and limitations which we saw with traditional networks. Because to start with, we are using basic networking at the moment for our deployment. That's a pretty rare use case because most of you will be using advanced networking, but our use case is we're an internet-facing company. All the virtual machines which you deploy with us get a public IPv4 and a public IPv6 address. So for us, there's no need to put virtual machines behind NAT boxes and do address translation. We want to have all the services internet facing because we are a public cloud provider. Everything goes on the internet. However, basic networking has its limitations. We had customers coming to us saying, well, I want to run virtual machines with you, but I want to run my own IP space on those virtual machines. So you are providing the virtual machines, but I want to use my IP space, which is on my name. If I would ever want to leave you, I could take the IP space and move to a different cloud provider. If they offer such services. And we were running into multiple problems with basic networking. If you started adding more IPv4 ranges, the DHCP server inside the virtual router would get so many entries, it would become very slow on startup. So some sharding mechanism to have multiple VRs would be a lot better. So you would say, let's go to VLAN. However, L2, packet tagging, but there's a limit of 4K VLANs per network. For us, per data center, well, it's not sufficient, it doesn't scale. However, the 4K might be enough, but it is very difficult to scale a layer 2 network. Making it redundant, spanning tree, all that stuff, you don't want to do that. It's a hassle to get a layer 2 network to stretch out in a big cloud environment. But it is very well implemented in hardware and in software because it's one of the oldest technologies which we have on Ethernet. Looking at VXLAN, I just copied this from Wikipedia, so I didn't type this. It's a much more flexible solution. We are encapsulating packets inside UDP, putting them on a regular layer 3 packet, and routing them through the network. So although it seems like layer 2, it is actually layer 2 packets encapsulated inside layer 3, and we're sending them through the network. But I created a different slide saying, in short, Ethernet packets encapsulated inside UDP. This means you can route them through your existing layer 3 network. So you can use all the technologies you want to make your redundant layer 3 network, make it flexible, scale it out the way you like, and the VXLAN packets are just routed through your network. It requires that the MQ of the underlying network is bumped to anything bigger than 1580, but we're just running with 9K. We just bumped to jumbo frames and all the hypervisors and running with VXLAN with it. VXLAN segments are called VNIs. I think it's the Virtual Network Identifier. That's the acronym. So instead of VLANs, you'll have VNIs, which you have. So for CloudStack 4.12, we improved the VXLAN support. It's actually pretty simple. On the hypervisor, there's this shell script being executed. If you start a virtual machine, it calls the shell script modify VXLAN.sh with a few parameters, and it sets up the VXLAN interfaces and the bridges on the hypervisor. Yes, we are using Linux bridges for our hypervisors. That script hadn't been touched in 6 years. So it was still running all the brctl things, ifconfig. It was just not using the IPv2 functionality of the kernel at all. So we rewrote the script. Functionality stayed the same, but it's now using the new IPv2 stuff of the kernel, just using the IP command. And we added IPv6 support for shared VXLAN networks. Security grouping is supported. Because we are a IPv6 company, all our services, they run on v6 by default, and we do v4 when we need to. So if you deploy a virtual machine with us, you'll get a v4 address and you'll get a v6 address by default. There's no need to ask. However, our internal infrastructure is v6 only. Our hypervisors are v6 only, our storage systems are v6 only. We're using Ceph storage for all our deployments. We have a lot of Ceph systems running, a couple of tens of petabytes of Ceph storage. That is v6 only. So we are a v6-minded company, switches, routers, all being managed over v6, and we're only using v4 where we need to. Where the end user is requesting, I need v4, which is usually in all virtual machines. However, we try to stay away from v4 because there's a shortage. You won't find any internal IP space in our company. No 10.x or 172 addresses. It's all public IP space and public routable. However, there's a shortage of v4, so we're doing v6 only. 4.12, we had a presentation, but there's more in 4.12. There's live local storage migration supported with KVM. So you've got 2 hypervisors with local storage with KVM. You can now live migrate a virtual machine from one hypervisor to the other hypervisor without the need for shared storage using live migration. And the stats collector already had an output for Graphite, but it now has an InfluxDB output as well. So all the statistics of your virtual machines and hypervisors can be sent towards InfluxDB. Our main focus was VXLAN support and the IPv6 support for shared networks with security grouping. So we had a project called internally, it is still running, we're building it out right now, called Compute 2019. It's our new iteration. We're moving away from basic networking towards advanced networking with VXLAN due to the limitations we had with basic networking. So we also bumped the hardware we're using. We're a Supermicro company, everything is running on Supermicro. So we're now using these new blade chassis from Supermicro to deploy on. They're pretty big beasts. 1.5 terabytes of memory, 10 of those in one chassis, so 15 terabytes of memory in a single rack, and that's consuming about 6 kilowatts of power. So yeah, you see a full rack with just one blade chassis in it, consuming all the power for the whole rack. Those are the ones which we're using. So for the local storage, 8 times 4 terabyte NVMe in there, and there's a 25 gigabit mezzanine card to get actually. Interesting part is, this is a Mellanox card, it has VXLAN offloading in the card. So Supermicro has this mezzanine card which you put in, and it offloads your VXLAN packets. So it's not your CPU handling the packets, it does the decoding of the VXLAN packets, and then gives them the raw, not the raw packets, but the decoded packets go to the kernel. So since we are using Supermicro hypervisors, we are now also moving towards Supermicro switches. I couldn't find a higher resolution of these, but this is a 32 times 100 gig switch from Supermicro. It's actually not a switch, it's a fully fledged router, but we're using ONI. So we are using Cumulus Linux running on top of those switches. Who of you has ever heard of open networking? And who's using open networking? Nobody. Oh, I see one hand slightly going up. Okay. Now, as the hypervisor is open source, the storage we're using, Ceph, is open source, or we're using local storage, but we had this last thing, the network, which you would just go to a vendor, get crappy software on their routers or switches, needed to buy very expensive licenses, and then they would say, it's end of life, buy my new router. Always very difficult. So we wanted to go to something different. There's Cumulus Linux, yes, they have licenses as well, but it's actually support which you're buying from them, because it's very difficult to say, hey, this is Linux, you need to pay for this to use it. Otherwise you can't use it because it's open source software. So it's a Debian-based distribution. You just log into your switch to SSH and you get a Debian CLI and you just have a few commands from Cumulus, but it's just a Debian CLI there. A very broad range of features, proper VXLAN support. But the interesting part about ONI is, although it's running Debian, it's just programming the chipset. So the packet switching and routing, it's all done by the chipset. And the chipsets in those switches are either Mellanox, Intel, or Broadcom. But usually Broadcom or Mellanox. So although we buy switches from Supermicro, I was Googling around a bit to find for the same features, and I just found this Chinese switch with identical specifications.
Quanta?
Not Quanta, no. FS.com, Quanta probably has the same ones. Everybody's buying the same chipsets, rebranding them and putting a label on there. The reason why we went for Supermicro is that because we have these hypervisors, and if we run into any complications on a layer 1 or layer 2, we can say, hey Supermicro, your stuff is not working, fix it. That's the main reason we went for Supermicro, and of course we get a discount because we're purchasing a lot of their hardware. So we get the freedom to actually connect. So what are we building? So we got two 100 gig routers running in a zone. At the moment we have two blade chassis. These blade chassis have internal switches, but they're just in layer 2 forward mode, forwarding all the packets from the blades towards these 100 gig switches. This is all 100 gig, and then we have our Ceph systems just being attached with 100 gig network. Yes, these are Juniper switches because we just have a bunch of them lying around, and we have a good deal with Juniper. They just do the stuff they need. But the main focus is for us is the VXLAN termination on these Cumulus ONI switches on top. So we're using VXLAN with BGP EVPN that you see up there. Layer 3 goes onto the Linux host towards the hypervisors. So how are we doing this? We're using BGP, which distributes all the VNI members and the MAC addresses to all the different hypervisors. So there's no broadcast or multicast running, which is broadcasting which MAC addresses or multicasting the MAC addresses. Who has used VXLAN before I go over this topic? Normally you would define a multicast group for VXLAN, but if you start scaling out with a lot of groups, you'll get a lot of chatter between your hypervisors, sending out all the, how would you call it?
Resolution.
Yeah, a detection or finding the MAC addresses, the members of the VNI, and it becomes a lot of chatter between the hypervisors. We are using BGP to distribute the VNIs and the MAC addresses. So we have BGP running on each hypervisor. So it is layer 3 until the hypervisor. There's layer 3 on there. So there's no layer 2 going towards each hypervisor. Layer 3 only. You'll see just the Quagga running on the hypervisor. We're using IPv6 for packet transportation. BGP is v6 only. That is v6. Ceph systems are v6 only as well. IPv6 going here. And then the virtual machine IPv4 packets or IPv6 are encapsulated inside these v6 packets from the hypervisor being sent towards the router. It decodes the packets, and using regular BGP, they are sent towards the internet. So the VXLAN stays between the Cumulus switches and the blade chassis. Our scaling benefits here. We have two blade chassis with 20 hypervisors. We can keep adding and adding and adding more blade chassis and more hypervisors. And BGP will just make sure all the hypervisors are updated with all the VNIs and the members of the VNIs. Since it's v6 only, everything just is routed through BGP towards the routers. Layer 3 is used. We're using BGP path detection, fast failover on the hypervisors. If something happens, we're flexible. So there are no VLAN tags going towards all the hypervisors, nor is there any layer 2 connection. Of course there's a layer 2 connection, but just for the BGP. No VLAN tags between these routers. That also allows us, because we're not using specific features of a specific switch. These are Supermicro now. We could take those out, put a different vendor in there, put Cumulus Linux on there again. Same configuration, it would keep working because it's all layer 3. To do BGP and EVPN, it requires a slight modification to this shell script, which I talked about when a virtual machine is started, the modify VXLAN.sh. The current VXLAN implementation uses multicast groups, which works, but for BGP, EVPN, you just need to configure the VXLAN interfaces slightly different on the hypervisor. And I didn't see a very easy route to implement this globally in CloudStack because it's so very dependent on your network setup that we just went with the route, okay, we're going to override the modify VXLAN.sh script on our hypervisors targeted towards our needs. It's on GitHub, I can share the script with you, no problem. You'll just see 3 lines being modified and a blog post which actually explains how you do this. But that's what we did, a very slight modification on the hypervisors to get that done. But what does it mean in practice for us? Well, we can offer what we call virtual private clouds to customers. They say, hey, I got my IP space. We'll start announcing your IP space on the internet. We'll just create a virtual network inside CloudStack with your IP space. The virtual router is spawned, handing out DHCP. Your virtual machines get an IP address which is on your name. Nobody will see where actually your cloud provider. If you do a trace route, you'll see our network in the middle before you end up with your virtual machine. But it's not guaranteed that you are running on our infrastructure. All the networks we create have one IPv4 and one IPv6 subnet. Usually the maximum for v4 we use is a 23, so that's roughly 500 addresses. One virtual router, 500 DHCP addresses, entries. So the VRs can stay pretty small. We have the sharding. If one VR becomes a problem because they're only doing DHCP, we just kill it and a new one starts up. So we have a lot of VRs running, but they're not that big. It allows us to scale to a very large amount of virtual networks. That's the brilliant thing about VXLAN. You can have 16 million VXLAN networks inside one data center. 16 million is a limit we're never going to reach. Even 4K would have been a very, very high number. But layer 2 scaling is difficult. VXLAN makes it a lot easier. And of course, the higher redundancy. We're using BGP. Failover is easier, it's faster, and it's more flexible. If we want to add additional network connections to a hypervisor, should it be needed, BGP will pick it up and just route the traffic over the most efficient route for us. I do have a few things to demo, because before I go to the next slide which says thanks, I can show you a few of the things you'll see on our hypervisors. I have this POC setup running, where I opened my browser already. So I hope. This is just a demo setup. This is one of the proof of concept setups which we have. So what we did here, which you can see, I created my own private cloud here. In this case, indeed, I'm using private IPv4 space for this virtual network. It's just that we're also offering to a few customers who say, hey, I want to have a site-to-site to my premises using IPv4 space, which is RFC 1918. We're not terminating that in CloudStack. On a higher level in our network, we have site-to-site devices where we then connect the customer, and then just using regular BGP and IP, that traffic ends up at CloudStack. We're not having the VR doing the traffic. We'll have a static layered site-to-site connection somewhere in some Cisco equipment doing it. But otherwise, it's just public v4, public v6, public v4, etc., etc., etc. Or we just create a network without v6 if a customer says, I don't need v6, but we usually highly discourage people to not enable v6. And you can just keep adding those networks. And it's just as simple as you would like. You would just fill in the VXLAN and the VNI, that's all. The VNI number, that's all. Then the BGP on the hypervisor will pick it up and start doing the VXLAN traffic. I'm sorry, wrong field actually. It should go there. Now, I had a terminal open as well too. case. In this case, this is VNI 2001. Yeah, there we go. So there's the bridge. In this case, we have two virtual machines attached to this specific bridge. And then there's one VXLAN 2001 device there. Now, I'll just set the font to something. It's just a VXLAN device. That's all you'll see on the hypervisor. Nothing special. It's BGP picking it up. So what I did on the this was the one which we rewrote for the release. Normally, the ones familiar with VXLAN would see on this line, there would be a group here, a multicast address saying you need to join this multicast group. If you set it to no learning, then you will actually tell the VXLAN device, if you don't try to learn this, we'll have a different mechanism doing the learning. And although I can tell you how this works, I stole a big part of this. No, didn't steal it. I just learned this by reading a blog post from somebody. BGP EVPN with Cumulus Linux. And it completely tells you how to set this up, what you need to do depending on what you're using. And here we see him say, IP link at VLAN type VXLAN, no learning, and you need to set a local address for that specific hypervisor. And then, of course, you would need to set the whole BGP stuff on the hypervisor as well, which does the learning for you. But here we go, address family EVPN, advertise all VNI, advertise all the virtual network identifiers of the VXLAN. And then traffic is routed to all the hypervisors. So for CloudStack, CloudStack is totally not aware of the BGP nor the distribution of the VNIs. We do this by modifying the VXLAN script. Now this script is called modify VXLAN.sh. If you want to override something like this, still, does anybody recognize this, that there's garbage in the CloudStack agent log? I don't know why it gets in there. So the thing you can watch out for, I know it says modify VLAN.sh, but that's not the point here. It will find the script modify VLAN.sh, but if you put it in one of these other locations, so user share modify VLAN.sh, you're not overriding the file which comes with CloudStack. You're just putting it in a different location, which is then picked up by CloudStack, saying, hey, I'll use this script instead of the script provided by me. So that's what we're doing. We're using Salt in our case, not Ansible or Puppet, we're using Salt, and we're just putting that file on the hypervisor, saying, hey, this is the modified file which applies to our network configuration. And we are now using that one which has the BGP modification for us. So that was actually my talk. Donald's, I probably used way less time than expected.
Keep going.
Yeah. Sorry. Any questions so far?
Do you use Quagga for BGP?
Yeah, we use Quagga
on hypervisors.
On the hypervisors, yes.
Okay, and since your infrastructure seems to be pretty capable to provide layer 2 services between virtual machines, do you have any requests from customers about layer 2 connectivity or layer 2 services?
Yeah, we do get those questions, but we try to not do customized work for customers. So we're a small team, and we try to offer the same services over and over and over and over. That's the easiest way to scale. So although there are layer 2 requests, that is usually somebody coming from what we call an enterprise legacy environment, but it's not a cloudy environment to go to tag in layer 2. So we try to stay away from layer 2 networks. The same goes with multiple IPv4 addresses per VM. Yes, we do offer this to some customers, but we discourage users to have multiple addresses v4 or v6 per VM, because then we say deploy an additional machine running that service. So in layer 2, we try to stay away from layer 2.
Okay. And where are the virtual routers then in this infrastructure?
Yeah, so your question is, where are the virtual routers? Well, they are co-located on the same machines. So the virtual routers are just started by CloudStack on the same hypervisors, and that's where they're running.
So, for example, you might have traffic coming from one virtual machine on one hypervisor, going to the virtual router on the other hypervisor, and then back to the internet.
So your question would be, does our traffic go through the VR? No, our traffic never passes through the VR. We are using shared networks, not isolated networks. So a virtual machine running on this hypervisor, if it wants to contact this virtual machine here, the traffic is sent through one of the two routers, BGP, and then it's sent back to this hypervisor. It does not go through the VR. The VR in our case only does DHCP and user data. It does traffic, although it's called the virtual router, traffic of the virtual machine never goes through the VR. So we're not using redundant VRs either, because DHCP is something you can lose for a few minutes. So, but it's not that all the VMs are requesting the addresses all the time.
So the gateway for the virtual machine is in these switches there?
These are the gateways for the virtual machines. Yes. So each VNI, the gateway address for a VNI, is terminated at these. For IPv4, we have a floating IP addresses. So there's usually the .1, the .2, and then the .3 address. That's the virtual one. With IPv6, both of them are sending out router advertisements saying, I am a router, I'm capable of routing, and there's no floating address.
So you said earlier, I can come to you and say, here's my IP space.
Yeah.
6 or 4, whatever, 6 in your preference. Please host it for me. And that IP6 space just simply ends up on the shared network that is effectively VNI isolated.
Yes.
Right, okay.
Yeah. So it is a shared network.
There's only one IP space involved, basically.
Yeah, there's only one IP space. So at least we need a /24, because the internet doesn't allow you to announce anything smaller than a /24. So for v6 we need at least a /48. But in each VNI we configure one /64. There's no need to go bigger than a /64, which is of course an enormous amount of space. So we limit the VNI to a /24 usually, or if you give us a /24, we could say, because we have multiple data centers in Amsterdam, we could say, well, let's say we're going to use a /25 in this data center, a /25 in the other data center, and then a /64, and it's up to you to say, I'm going to deploy my virtual machine spread out over the two data centers. All the data centers, they have their own management servers running. So it's not that we have one management server managing all data centers in Amsterdam, although it would be technically possible. We want to make sure that if a data center burns down, the other data center is not affected. So there is BGP, but there's no VXLAN traffic going between the data centers. They're completely separate failure domains. If the data center goes down, then those VMs go down. you need to deploy your VMs in 2 data centers with us to get the redundancy.
So I can't come to you and say, please stretch my IPv6 space between Amsterdam and Miami, for example.
No. But
Have
if
you
you
do
would,
2 spaces effectively.
yeah, they would give us 2 spaces. So the Miami network is not even the same autonomous system.
Yeah.
The Amsterdam network and the Antwerp network are the same autonomous system, but that's where we draw the line as well. They say we have different autonomous systems just to make sure we have the redundancy in the failure domains. So usually when somebody comes to us, they want to deploy virtual machines in different data centers because they want to have these availability regions. So technically it would be possible, but we stay away from it due to complexity and failure domains.
So basically I cannot move my virtual machine from one Amsterdam data center to another without changing the IP address.
No, you can't.
And the network.
No.
Okay.
Different question. So you're offloading all your VNI handling to your own switches at the top.
Yes.
How efficient is that? Do you still have CPU overhead down at the hypervisor layer to handle that, or is the hypervisor layer running just as cool or just as hot as it would with more traditional networks?
We see a slight CPU increase, but it's the mezzanine card on the blade, which is an additional card you can order from Supermicro, which does it's a Mellanox, a Connect X4 chipset, and that does the VXLAN offloading. That's supported in newer kernels, and if you use that chipset, it offloads the VXLAN traffic by a chipset on the Mellanox card.
Without this offload, there is a huge overhead, CPU overhead.
Yeah.
Without
Yeah.
this offload.
Because it needs to decode all the
Yeah.
UDP packets and fetch all the
And
stuff.
have you load tested it? I mean, a single hypervisor in your rack there, how many, it doesn't have the concept of VNI anymore, or does it still have the concept of VNI?
Well, of course, the hypervisor itself has a VXLAN, and I'll get to you in a second because your neighbor was raising his hand as well. So the hypervisor has, of course, the bridges and the VXLAN interfaces, but it's not that it's decoding the VXLAN packets. That's done by the Mellanox chipset inside the hypervisor. On average, the VMs we see in the public cloud are between 8 and 16 gigabytes of memory. You do the calculation, 1.5 terabytes of memory, divided by 8 to 16 gigabytes, you get, well, 200 virtual machines on a single hypervisor.
Yeah, so you're going to run out of CPU and RAM before you even get close to maxing out on the VNIs.
It's also that we're not aiming for all the use cases. We are not aiming for a gaming provider to run a virtual machine. We're not aiming for the voice over IP provider. We are mainly still in, although we are the cloud provider, we're still mainly in the web hosting business. And that's not that super latency intensive usually as voice over IP would be, or gaming would be, or any other on-demand live or live system instead of being an on-demand system. Yeah. Your name?
Partially answered what I was going to say. As a broadcasting network, if we're in outside the European side of things, and we want to, say, deploy your services, there would be a complexity for the IP addresses. I'll have to have 2 or 1.
Well, if you deploy on 2 locations with us, you get virtual machines with 2 different IPs, of course, and there's no way we can move those IPs between the data centers, or have the VM move to a different data center. So we offer higher level services, HTTP load balancing, which we do with Anycast, which then balance over your different virtual machines, but that's outside CloudStack. Although actually the infrastructure runs inside CloudStack, but it's not in the scope of CloudStack to do the load balancing for us. We have different services doing that. Paul?
You said you're doing this on Linux Bridge, so why is the choice of Linux Bridge over OpenVSwitch?
History. It works for us, so we haven't, it's still on the list of things to investigate if we want to go to OVS. But for now, the bridges are still functioning. It might be that we run into, when we have a very high amount of packets per second, that it might be interesting to go to something different, but then Mac VTAP also might be an interesting thing to investigate. I don't see any questions or hands going up, so somebody wants information on running Ceph with CloudStack, that's what we're doing as well. We have our NVMe only deployment, so we will, because I heard Mike from Ticketmaster say, well, Ceph didn't work for us. Well, I'd like to have the discussion with you why that didn't work. So, it works brilliant for us.
Like about scale? Like what's your latency, like what scale, all of that stuff?
So with Ceph, the latency we see with the newest systems, and then we do 3 times replication. We're running full NVMe only, we're not using HDDs anymore, full NVMe. The latency we see with writing a 4K packet, synchronized IO depth 1, the latency is 0.7 milliseconds.
0.7 milliseconds.
Point.
700.
So 700 nanoseconds. Microseconds, yes, that's the big difference. Microseconds for a 4K write.
It's a little bit nicer than 20 milliseconds.
That's a lot nicer than 20 milliseconds, yes. But it does require some CPU tuning to get there. So you need to have the right CPUs and the right configuration for Ceph, and then we can get to the Ceph.
What network is this?
10 gig. Just regular 10 gig, nothing special. Actually, you see it here. It's a QFX 5100 48T from Juniper, and then we have Supermicro systems, one use with 10 NVMe's in there, 96 gigabytes of memory, dual 10 gig connection, going to the Junipers and then going towards the Blade chassis.